The James Webb Telescope has now taken another image that shows that something is seriously wrong in our universe. Either our space is going crazy, which means it has some kind of intelligence, or our scientists just got it wrong. The fact is that since the launch of the new telescope, we have experienced a crisis in world science, the likes of which we have never seen before. New discoveries seem to be trying to tell us something urgent, but so far scientists argue more than they can present us with real new facts and truths. Does this mean the end of everything? No stone has been left unturned since JWST showed us images of galaxies so old and perfect they shouldn't even exist. This was the beginning of the drama of modern science, which continues to this day. More and more images show even more crazy phenomena and impossibilities. Nothing in the young universe is what scientists thought it was, and it is also now clear that the entire universe is not what our scientists thought it was. Scientists have assumed that the universe is homogeneous, meaning that its large structures are largely uniform. But now there are dozens of indications that the universe is in fact inhomogeneous, challenging some basic assumptions about the nature of the cosmos. The idea of a homogeneous universe goes back to early 20th century cosmology. Albert Einstein introduced the cosmological constant in his general relativity, describing a static universe that neither expands nor contracts. A little later it became clear that we do not live in a static universe, but this space with all its phenomena is very dynamic. There is nothing in this universe that does not move. However, physicist Alexander Friedmann concluded that Einstein's field equations also work with an expanding or contracting universe. Georges Lemaitre then proposed the idea of the Big Bang, where the universe expanded from a single point. This development led to the idea of a homogeneous and isotropic universe anchored in the so-called cosmological principle. Basically, the universe is homogeneous and isotropic on a large scale, meaning it looks the same everywhere you look. Let's compare it to a landscape. A homogeneous and isotropic landscape would be like a vast endless desert, with sand evenly distributed everywhere and without hills, valleys, or other geographical features. No matter where you look or where you go, the landscape looks the same everywhere, and there are no recommended or special places. In the case of the universe, this would mean that stars, galaxies, cosmic nebulae, and other phenomena are broadly evenly distributed in space. However, recent discoveries by the James Webb Space Telescope and other astronomical observations have shown that the universe may not be as homogeneous and isotropic as previously thought. Quasars and the Great Ring prove it. It may seem strange to imagine the entire universe as a landscape, but on closer inspection, the idea is not so far-fetched. Only the measurements are slightly larger. Here we have galaxies with millions or billions of stars. They travel around the universe along filaments and gather in groups. We know about giant empty spaces, vacuum, black holes, and other phenomena. All these objects take part in the cosmic spectacle. Scientists have now discovered that one side of the sky has about 0.5% more quasars than the other. Quasars are ultra-bright galactic nuclei powered by supermassive black holes. Such an uneven distribution further indicates that matter in the universe is not evenly distributed. Another discovery, which speaks against the theory of a homogeneous and isotropic universe, are two very large cosmic structures, the Great Ring and the Giant Arc. These structures are formed by galaxies and galaxy areas. These structures are so large that they exceed the scale at which the universe should be homogeneous and isotropic. Basically, they are so large that our measurement techniques fail here. Such megastructures indicate that the landscape of the universe has something akin to high mountains, and no one currently knows how they formed or how they fit into the overall structure. But these are only the latest discoveries that are slowly but surely strengthening the suspicion of a heterogeneous universe. Before these latest exciting discoveries, there were already signs of the universe expanding at different rates. Here, methods of measuring the expansion rate of the universe have given mixed results. We know this difference as the Hubble tension. If the universe is not the same everywhere, that would explain why it is not expanding uniformly. Somewhere between the cosmic background radiation and the seeds, there may be a previously unknown layer or force of the universe that is responsible. Dimensional differences, or the universe, do not expand uniformly because somewhere there is a cosmic mountain in the way. The new telescope has a role to play in the current research, as scientists use the James Webb Space Telescope to confirm Hubble's excitement. Why does cosmic background radiation show a uniform distribution of matter? Do you want to know a really curious fact and an amazing theory? Let's take another look at the cosmic background radiation, or CMB for short. This does show a uniform distribution of matter. The CMB is considered to be the afterglow of the Big Bang and is basically constant microwave radiation. The radiation began about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine to form neutral hydrogen atoms. This moment is called recombination. Before recombination, the universe was a hot, dense plasma made up of ions and electrons constantly colliding with each other and scattering photons. These constant collisions ensured that the matter and radiation of the universe were tightly coupled and in thermodynamic equilibrium. During this time, the dense matter scattered the radiation strongly, preventing it from traveling long distances without the particles colliding. As the universe expanded and cooled, the temperature eventually dropped below about 3000 Kelvin, allowing electrons to combine with protons to form neutral hydrogen. This process drastically reduced the number of free electrons, making the universe transparent to photons. Photons could eventually travel unhindered. Light was born, and the separation of matter and radiation continued. These released photons are what we see today as the cosmic background radiation. The uniform distribution of CMB radiation has led scientists to believe that the universe is nearly homogeneous and isotropic. It may have been over 13 billion years ago when it was smaller. But now imagine what if the universe did not expand in empty space, but in space where something already exists. The Big Bang and the distribution of matter soon after may have been homogeneous, but then the expanding universe created obstacles that disrupted the homogeneity. These obstacles can be many, but they all lead to fantastic theories that delight space fans but give scientists headaches. The old knowledge about the Big Bang says that space came into being only with the Big Bang. The expanding universe is space. According to old theories, there is nothing outside of space. Quantum physics has already shown that nothing can exist, and quantum physics has shown that a multiverse with many nested dimensions and countless universes of different shapes, sizes, and natures is more likely than the single universe in which we live. What if our universe expands into space with other universes, dimensions, and previously unknown structures? This would of course mean that it would encounter obstacles, send other universes or dimensions as it spreads, or oppose our universe. The initially homogeneous Big Bang then became inhomogeneous as a result of these encounters. Such considerations are fascinating, but despite many inconsistencies in astrophysics, they currently do not receive official attention. Is our own Earth the proof? You won't believe it, but some brave scientists who support theories like the multiverse have come up with an interesting comparison. Our Earth also began as a homogeneous world. Early planets are masses of gas and dust, just like early suns. Then, they slowly evolve, become more independent, take individual form, travel around the solar system, collide with other celestial bodies and change. In the beginning, the Earth was a glowing hot ball, and matter was evenly distributed.